And then for analytic functions, we have this nice formula. So you have to integrate over the contour, right? F of t, z minus t. You have this formula, but the integral goes over the complex variable, over the contour. So if we plug in here the matrix, we get this resilient representation. And this is probably the most general way, the right way to define what a matrix function. When I stand up and switch off, right? So this is the most general way of deriving what is a matrix function. Why? So the way that we define it, for example, using eigendecomposition, the way that we define it using Schur form, the way we define it using Schur form, it still requires that eigendecomposition exists. It still requires that the Schur form exists. We know that it exists for finite dimensional problem, but we can in fact have any operators in an infinite dimensional space. This can be, for example, a differential operator. And when we are solving partial differential equation, we have d over dt equal the differential equation applied to the function. And these definitions are not translated directly to the infinite dimensional case. So polynomials can be extended. We know how to multiply operators. This is just a composition and so on. We can define what is an inverse of an operator. So, and this formula can be nicely translated to the general functional analysis setting. This is the formula that only requires that we know how to compute the inverse, we can define. And this is also, in fact, in many cases, a very nice computational tool, because if we manage to come up with a good contour, and then approximate this integral by a quadrature, a few number of terms, then we will get an approximation of the matrix function misprint here should be P.4. As a sum of so-called, well, this is called resilient of the matrix, as a sum of rational function, and this can be a very good approximation actually, with very few number of terms. It depends on the distribution of spectrum. You need to know where the spectrum of your operator lies, but this is a very good way of constructing computable approximations for general matrix functions. So you need to design the contour, you need to design the quadrature, but after that you have the formula, and in order to multiply this matrix function by vector, you need to solve these linear systems. And since you have this tk, which can be actually complex shifts, and if you make complex shift, often you improve the conditioning of the matrix, because you are basically moving in the direction that is orthogonal to it's okay, now you need to use complex arithmetic and so on, but this is actually a very useful computational tool, and we actually, I recently encountered it. So what we are doing for some project, so this was for testing. Okay, the question was, let's approximate the matrix exponential by polynomial, right? So how we can parameterize the polynomial? This was around the lecture about Chebyshev, so let's try to approximate polynomial just by polynomial. So time stepping. Let's find optimal time stepping. No problem. So what people that are influenced by machine learning do, they formulate the optimization problem, the left side minus the right side, and optimize over the roots. Seems to work, PyTorch will run. Well, first of all, I took exponent of a t, where t was small, 10 to minus 3, so it's a small time stepping. And the answer that I got from the optimization procedure was that all TK are the same. So I only got a trivial approximation to the matrix exponent, which is just an explicit Euler scheme. Okay. The next step, okay, was let's try to approximate the polynomial in the basis of polynomials. Say with Chebyshev polynomials. Then this is just a least squares problem. You immediately get an approximating polynomial, and this approximating polynomial that you get is much, much better than explicit Euler scheme. So here the error might be 10 to minus whatever 4, here is 10 to minus 2 orders of magnitude difference. So what's the problem? Okay, this is a nonlinear, this is linear, so probably there is a some local minima and so on, but after several days, well, I have a lot of other stuff to do for sure. But then I decided just to compute the polynomial and compute the roots of this polynomial. And for small t, all the roots of this polynomial were complex. So I was trying to find optimal parameters here, but the optimal parameters are actually complex. The roots are complex. So, yeah. So that actually means that then, and now when I'm telling you that I just understand, in order to compute these parameters, I just need to take this formula, take the quadrature of the complex plane, and get exactly good roots. And they look actually quite nice, these roots there. So they're located in the complex plane, something like that. Like this. Of course, you have to have complex conjugated. So probably this is the way how this optimal rational approximation with complex time stepping looks like. Okay, this is sort of lyrics. Let's go on. Should we make a break? Should we make a break or just continue to the approximation? Should we make a break? Should we don't make a break? Yeah. Let's go on. And just finish maybe a little bit early. Okay, the main thing, but this is not purely, stupid math. This is actually the way of getting a very good approximation, but you need to find out the optimal contour of the complex plane. Maybe you can parameterize an optimal contour and optimize it and so on to find it, because, well, it's typically done just by drawing a random contour. So, besides matrix exponential, there are important functions. So, matrix exponential, if you have wave equation. Wave equation is very important, for example, in imaging, in oil, and many other places. So there you solve second order equation here. And the solution is given by the cosine of the matrix and the sine of the matrix, just as the scalar case. So an interesting case is the so-called sine function, which is actually non-analytic and so on, but you can define it. So the sine function, well, in the scalar case, I don't know if I have examples here, but okay, let's just draw it. If I have the examples. So the sine function is actually very important. Sine of A. So sine is just this function. So it's not defined for matrices which have zero eigenvalues, otherwise it works quite well. Let's take the sine of the real case, and what it is used for. So basically, if it has real eigenvalues, if a matrix has real eigenvalues, it puts all lambda k's that are positive to 1, all lambda k's that are negative to -1. So if you take the sine of A plus 1 over 2, so it puts all the positive to 1, all the negative to 0, and this is the projector. And then you get the matrix, like, okay, let's be diagonalized for a second. U star, which is an orthogonal projector onto the subspace spanned by positive eigenvalues. And this is important, for example, in modeling of dynamical systems. Okay? This is the sine function. Another So you probably know what is a Gaussian distribution. Who knows? Who doesn't know what is a multivariate Gaussian distribution? Everyone knows. So Gaussian distribution is parameterized by the mean value and the covariance matrix, which is positive definite. Right? Now the question, how to sample from a multivariate Gaussian distribution? If you know how to sample from a standard normal distribution, how we can sample from a distribution with a given covariance matrix? But okay, you have the matrix. So I give you the matrix maybe 1,000 times 1,000. This is my covariance matrix. How to sample from a Gaussian distribution with this covariance matrix?
You can sample from normal distribution with zero.
With 0, 1. That's what I can sample. I can sample the 1,000 divided, but it has identity matrix, right? So what I have to do with the sample to make it So if you make, so sample from normal, and then multiply by square root of the matrix, right? Then the expected value of okay, matrix is symmetric, therefore transpose is the same. So this is just, so we need to multiply by the square root of the matrix. We need to multiply by the square root of the matrix. Well, another way might be computing Hayetsky factorization of A, and then we can multiply by the R factor. Then the situation will be the same. But also multiplication of it. So we don't need the full matrix function. We only need to multiply the matrix function by vector. But this is, well, this is not trivial. For example, if you just have, and there are cases where you need to sample really from high-dimensional Gaussian distributions. For example, if you have a Gaussian random field, and the field is an image. So each initialization is maybe 256 times 256 image, and there is a covariance function between points. Then this matrix is a Jobless matrix. And you need to take a square root of a Jobless matrix, but even solving linear systems with a Jobless matrix is not an easy task. And this is actually a non-trivial thing how you can sample. So there are ways of, even for Jobless, you have to embed it into a circle, but now embed it to a circle, but in a positive definite circle. It's not so trivial how you can do that. And then you can sample. Or you can compute just the matrix, the square root of matrix times vector, using the methods that we'll probably discuss in this. So this is a basic task for quite a few applications, sampling from a multivariate Gaussian distribution with a given covariance matrix. And the typical case, if it's an image, it's a very large vector. And sampling is not so easy. Even sampling is not trivial. Okay. So now so what we've talked, Schur method and so on, this is of course about dense matrices when you need to compute the matrix function for a small matrix for which the general eigendecomposition of the Schur decomposition can be computed. If you go to large scale problems, it is not possible, but since we have this polynomial approximation, well, let's use Krylov methods. And of course Krylov methods are the most efficient methods for computing the action of the matrix exponential. Yeah, so that's actually this idea that I asked at the beginning. If you use -30 and if you have 1 million terms, that's the error. It's not even 100, but even with million terms, there is no approximation to the matrix exponent using Taylor series. So what we can do, So this is the method one, and this is a very nice method actually. So we generate a kernel subspace. How we generate a kernel subspace? We generate it using R-noisy recursion. So we generate an orthogonal basis in the kernel subspace, and then we do an approximation. An approximation is that we need to approximate the function of Q, H, Q star. A is approximated by the function of this. Okay, bounding the error is now a non-trivial task. Actually, for matrix exponential, it's not so. If our goal is to compute the action of the matrix exponential times vector, so for linear systems, it's quite clear how we measure the accuracy.